Hello everyone, my name is Leandro Iannacone and this presentation is about the modeling of the deterioration of bridges due to earthquakes using stochastic differential equations. So the deterioration processes that act on engineering systems can be classified into gradual processes and shock processes. The gradual processes cause a change in the state of the system over a long period of time. Think, for example, of chemical reactions or fatigue phenomena. On the other hand, shock processes act over a short period of time and cause sudden changes in the state of the system. So, for example, the occurrence of disastrous events such as earthquakes and floods. Different probabilistic formulations are in general available to model the changes that are due to gradual and shock deterioration processes. Focusing on shock deterioration processes in particular, the changes due to shock processes are generally modeled with discrete jumps at the time of the shock occurrences. Our goal in this case is to find a change in the set of state variable which we define by x, by the letter x, delta x. The way we do this is by using aggregated measures for shocks. So for example, the peak ground acceleration or the spectral acceleration for seismic motion. However, by using aggregated measures, these models are not able to capture the effect of the specific time history of the shock on the state variables of the system. In fact, different time histories might produce different changes in the state variable delta x1 or delta x2. And these real-time effects due to the time histories can only be captured with sophisticated models, for example, finite element models, which in general are computationally expensive and do not come with the associated uncertainties. So the goal of this presentation is to develop a probabilistic model that is able to capture this real-time deterioration of the system, and it also comes with the associated uncertainty. Focusing on earthquakes in particular, the models described in this presentation can be used in combination with ground motion prediction equations, or GMPEs. There are methodologies available in the literature that allow for the simulation of synthetic main shocks, for example, the one by Razayan and Derkurigan, but also main shock and aftershock sequences, for example, the one by Hu et al. So with this proposed new model, we would be able to make full use of these ground motion time histories to predict the evolution of the system during both the shock and after the shock. So the model that we come up with combines the effects of gradual and shock processes in a unified formulation, providing a useful tool for the life cycle analysis of engineering systems. This is the outline of the presentation. I will first start with the mathematical formulation which makes this possible, and then I will go over a simple numerical example, and then I will provide conclusions and future work ideas. At the University of Illinois, we developed a general framework to obtain the time-varying probability of failure for the system. In this framework, the deterioration of the system is modeled as a consequence of external conditions, which include shock occurrences, and then gradual deterioration and shock deterioration affect the evolution of these state variables x. In order to capture the possible interactions between processes that affect the system, we use state-dependent models. And the changes in the state variables then will lead to changes in the capacity of the system as well as in the demand of the system. Once we have time-varying capacity and demand for the system, then these can be used to estimate corresponding deterioration at the performance level and predict time-varying quantities of interest, for example, the most important, the probability of failure of the system over time. So for the purpose of this presentation, I will be focusing on the modeling of the state variable and in particular on the modeling of shock deterioration. In general, the evolution of the state variables is commonly described with discrete formulations. So these discrete models that are used to capture the evolution of the system over time, however, have a series of disadvantages. For example, there is no closed form solution available, the parameters for this model depend on the chosen discretization for the time domain, and then the calibration for these models might be computationally expensive. So what we do is we propose a new formulation that models the evolution of the n-state variables with a system of stochastic differential equations. Here I'm showing what a typical stochastic differential equation looks like. We have the sum of two parts. The first part is the product of a drift coefficient and the infinitesimal time change dt, and this is the part dedicated to quantifying the deterministic change in the state variable over time. And then the second part is the product of a diffusion coefficient sigma and a driving noise, ds. And this is the part dedicated to quantifying the uncertainty. So in general, this driving noise determines how our evolution of the process over time looks. This is a continuous formulation, and it helps overcome most of the limitations that are posed by the discrete models. So for example, the unknown parameters of the model no longer depend on the discretization that we choose for the time domain. We can use results from stochastic calculus, which is also known as ethos theory, for the simulation of the stochastic processes. It is possible to seamlessly combine the effect of gradual and shock deterioration in a compact form. The model reflects the true nature of the processes, which is a continuous nature, and then closed form formulations are available for reliability analysis. For example, the formulas for outcrossing rate. This continuous formulation also allows for a new interpretation of shock processes. In fact, if inside these drift and diffusion coefficient of the stochastic differential equations, we insert explanatory functions that are related to the time history of the ground motion of any shock in general, then we would be able to capture the real-time evolution of the system during the shock. And if we use this sort of formulation, we are basically looking at shock processes as short-time gradual deterioration processes. And our driving noise can be a Brownian motion because we don't need jumps in the process anymore. So the calibration of these models can be performed based on available data, and this available data can be collected from the field, for example, using structural health monitoring or non-destructive testing procedures, or it can be obtained with sophisticated finite element models. Independent of how we collect this data, once this data has been collected, the unknown parameters in the stochastic formulations can be calibrated using one of several methods available in the literature, some of which using the maximum likelihood estimation method. As an example, we show the following structure, which was subject to a collection of ground motion time histories. In this case, the bridge is a single column band following a specification from Caltrans, and the selected ground motions are characterized by similar aggregated measures, but different time histories, in order to capture how these different time histories affect the evolution of the state variables over time. For this example, we collected data from finite element analysis, and we use this data to calibrate the probabilistic models. In particular, we use the OpenC software, which is a finite element software, and we recorded the evolution of the first natural period of the structure under different time histories. Here, for example, I'm showing the effects of two different time histories on the evolution of this parameter, which is denoted by Tn. Then we calibrated the model in the form such as the one that I showed earlier, and in this case in particular, the drift and diffusion terms of the proposed stochastic formulations were assumed to be functions of different parameters that are related to aspect of the ground motion, specifically to the instantaneous acceleration, ground acceleration, AT. This is the list of explanatory functions that were appropriately selected to capture the different aspects of the time histories. For example, the first four explanatory functions investigate the direct effect of the instantaneous acceleration AT on the evolution of the first natural period of the structure. Then the fifth explanatory function investigates the effects of the possible interactions between the instantaneous ground acceleration and the value of the first natural period itself, and this is what makes the formulation state dependence. And then the last two explanatory functions are included to capture the effects of the inertia of the system during the seismic excitation. Specifically, the sixth explanatory function captures the effects of the inertia in the past second, because it's the maximum value of the acceleration in the past second, whereas the seventh explanatory function is the maximum value of the ground acceleration in the past 10 seconds. So these are the results, and the results show agreement with the generated data. On the background of each of these plots, I'm showing the ground motion which was used to generate the evolution of Tn. The red line is the result of the finite element model, and the black line is the result of the stochastic formulation. And you see how the stochastic formulation is able to capture the evolution which is given by the red line, which is the finite element model. So concluding, available models for deterioration are able to account for the effect of multiple deterioration processes, both gradual and shock, and also their interactions, but the effects of shocks is generally aggregated in single time jumps. The use of stochastic differential equations to describe the deterioration processes can facilitate both the simulation and the calibration of the models, and it allows for new interpretation of shock processes as short-time gradual processes. By including parameters that are related to the time history of the shock into the continuous formulation, it is possible to capture the real-time deterioration of the system during the shock occurrences. The calibrated models are able to capture the changes that are due to the specific time history of the ground motion, whereas the commonly used models would only use aggregated measures. And then finally, these models can be used in combination with ground motion prediction equations to predict the performance of the system over time, and consequently incorporate these aspects into a more comprehensive life cycle analysis of the system. With that, I would like to thank you for your attention. These are the email addresses of both authors of this presentation, which are me and Professor Gardoni.